All right, so this is section 4.4 for precalculus, properties of rational functions. So what we're doing is, in this chapter, we're exploring how to find the zeros of a rational function and what it looks like on the graph. And we've talked about multiplicities and when we have odd and even functions. So in this section, we're going to look at rational functions. And these are going to be functions with a polynomial in its denominator. So a rational function, please just write this down. A rational function will have a polynomial in its numerator and a polynomial in its denominator. Obviously, Q is not a zero polynomial because we do not deal with zeros in the denominator yet. The domain is a set of all real numbers except those that make your denominator equal to 0. Denominator can't equal 0, so our domain is all real numbers except whatever makes our polynomial on the bottom 0. Okay, so our first learning objective is to find the domain of a rational function. Thankfully, we've been doing this for a while, so this should be pretty easy, pretty intuitive by this point. Find the domain of a rational function. So we have a rational function, 2x squared minus 4 over x minus 5. The domain is all real numbers except for negative 5. So in set notation, it's x values except, or x values as long as x is not equal to negative 5. Make it easy, right? The domain of, so on these ones, just write down the function and just write down the domain. If you want, you can also write down interval notation because a lot of times our practice is asking for interval notation. So for this one, it would be negative infinity to negative 5, both of those not included, union with negative 5 to infinity, both of those not included. The domain of r of x equals 1 over x squared minus 4 is a set of all real numbers except negative 2 and 2. If you want to find the denominator algebraically, just take the denominator, set it equal to 0, and solve for x. Okay, x to the third over x squared plus 1. There is no number that will make the denominator equal to 0. No matter what I plug in for x squared, it will never be negative 1, so it'll never add to the 1 and equal 0. So for C, it's the set of all real numbers. For D, the domain of r of x equals x squared minus 1 over x minus 1 is the set of all real numbers except 1. So all x values except where x is equal to 1. So I'm going to record that. Okay. So when you have a factorable numerator and a factorable denominator, and they cancel out, say you cancel out a term in your denominator, you still have to take into account what made the denominator 0 before you factor. That still is a part of the domain. All right, so now we're going to start graphing these little guys. So make sure you guys get your graphing calculators out or your graphing utilities. We're going to analyze the graph of h of x equals 1 over x squared. So the first thing we're going to do is we're going to look at some values. if I have x in the denominator only, and I put a fraction in there, dividing by a fraction means multiplying by the reciprocal. So if I put a fraction into my fraction, it makes it a big whole number. It flips it. So instead of this being 1/2, it's going to be squared. So it's going to be 1 over 1/4. And then 1 divided by 1/4 is the same as 1 times 4 over 1. So it's going to spit us out 4. If I put in 1 over 10, so as you look, these fractions are getting smaller and smaller. So if I put in 1 over 10, that's 1 squared over 10 squared in our denominator, so that's 1 over 100. And then 1 divided by 1 over 100 is 1 times 100 over 1. So that's why they get out 100. So as you look, the smaller my fraction gets, or the closer we get to 0, the bigger my y value is. So the closer I get to 0, think about this, the closer I get to 0, I'm getting down close, my y value is shooting up into the sky. The closer I target in on that 0, shoot up. And that's from the left-hand side as well. So the closer I get to 0, more and more high y values, large y values. Same thing here, the closer I get to 0, the bigger my y value is. The further away I get from 0, the smaller my y value is. And you guys can look these values up on your graphing utility. Hold on. Okay. Using transformations to graph a rational function. We know what 1 over x squared looks like. We just graphed it. So now we are going to graph a translation 2 units to the right and 1 unit up. So here's what our original 1 over x squared. We're going to shift that 2 units to the right and 1 unit up. So it moves our entire asymptote over to from x equals 0 to x equals 2 and shifted my y asymptote from y equals 0 to y equals 1. So when you're shifting rational functions, you guys only have to draw this one. The asymptotes that we are in our domain and range restrictions follow the shifting. All right, so to find asymptotes, we are going to look at the end behavior of our function. So if this is, please, this is not, don't write anything down. We're just looking. So we look at our 1 over x minus 2 squared plus 1. We're going to look at what happens when we put really big numbers in for x. You can see when I put in 10,000, we get out a number that's really close to 1. So as we get bigger and bigger x values on the right-hand side, that graph is going to swoop in and get really close to y equals 1. And then you go really, really negative. So on the really, really negative side, on the left-hand side, as we come swoop down, we're going to get really close to y equals 1. And then we want to look as we approach 2, because we know we can't equal 2, but as we approach 2, we're going to get really, really giant. So when we come in, I'm going to get closer to x equals 2, and it's going to skyrocket up. And then same thing from the other side. So this is approaching it from the left. We're going to approach it from the right. So starting at 2.5, 2.1, 2.2. We're approaching it from the right-hand side, and it's going to shoot up again too, which matches what we got for our graph. So the vertical line, x equals 2, and the horizontal line, y equals 0, are called asymptotes of the graph of R. So, if R is a function, as x approaches negative infinity, or as x approaches infinity, the values of R approach some fixed number L. Then the line y equals L is a horizontal asymptote of the graph R. If as x approaches some number C, the absolute value of R of x approaches infinity, then the line x equals C is a vertical asymptote of the graph R, and the graph of R never intersects a vertical asymptote. These are all two really important concepts. So end behavior as x approaches infinity, the values of R of x approach L. The points on the graph of R are getting closer to the line y equals L, and y equals L is a horizontal asymptote. Or as x approaches negative infinity, the values of R of x approach L. That is, the points on the graph of R are getting closer to the line y equals L, and y equals L is a horizontal asymptote. So you can do this both ways, either left or right. Here is your vertical asymptote. The points on the graph are getting closer to the line x equals c, and that makes x equals c a vertical asymptote. Or you can split it. They're either approaching negative infinity and positive infinity. So those are vertical asymptotes, the line x equals c. Then we got this guy. He's an oblique asymptote. He doesn't follow the normal conventions. He wants to go slant, which is okay. We're cool with that. We can handle it. This is an oblique asymptote. Okay, so we're going to find vertical asymptotes of a rational function. So now we're doing it. Now we know what they look like. We know what the graph does. We're going to find these guys. So to find a vertical asymptote, we are going to make sure our rational functions in lowest terms will have a vertical asymptote at x equals r if r is a real zero of the denominator. So if x minus r is a factor of the denominator of our rational function, then r will have a vertical asymptote at x equals r. So if I'm writing this down in my function, I say I go r of x equals p of x over q of x. Vertical asymptote at x equals r if r is a zero of q. That's how I would write that down in my notes. Okay, so we're going to find the vertical asymptote of the graph of each rational function. The vertical asymptote is when the denominator equals 0. So we say it is at x equals negative 3. So on our graph, we go to negative 3 on the x's, and we draw a vertical line, usually with dashed, to indicate an asymptote. H of x is x minus 3 over x plus 2 times x minus 2. So we have two vertical asymptotes, and they are at x equals 2 and x equals negative 2. So I'm going to have two vertical lines, usually dashed, to indicate the asymptotes. All right, f of x equals x minus 1 over x squared plus 5x plus 4. Remember in Algebra 1 when we did all those factoring polynomials and you're like, this is lame, when are we ever going to use this for anything? It's all coming back to haunt us. Algebra 1, thank you. So when we factor the bottom, we get x plus 4 and x plus 1. And then the zeros of that are negative 4 and negative 1. So x equals negative 4 and x equals negative 1 are those asymptotes. All right, last one because we don't have any more room on the page. X squared plus 3x plus 2 divided by x squared minus 4. We have to simplify this down into lowest terms. That's what the requirement said. So we simplify it into lowest terms. We get x plus 2 times x plus 1 on the top, and x plus 2 times x minus 2 on the bottom. The x plus 2's cancel, which doesn't mean that negative 2 is in my domain. It just means that there's not an asymptote there, but in fact there's a hole there. So leaving just x equals 2 as our asymptote. All right. If we graphed each of these guys, so 1 over x minus 1 has a vertical asymptote at x equals 1. If I go 1 over x minus 1 squared, it takes this part where there were negative values and pops it up above the x-axis. 1 over x minus 1 cubed, so this one still has a vertical asymptote at x equals 1. It brings this guy back, but you can see he is more tightly compacted to the x equals 0 asymptote. Then this guy has a wider curve. And the x minus 1 to the 4th 1 over, x minus 1 to the 4th, is same as this guy, but instead of as wide a curve, the curve gets more boxy. So each has a vertical asymptote at x equals 1. What happens to the value of r of x as x approaches 1 from the right side of the vertical asymptote? That is, what is the limit as x approaches 1 from the right, that's from the positive value, of r of x? So you want to look, what happens here? Oh, it gets, as it approaches, it gets bigger and bigger. As x approaches 1 from the left-hand side of the vertical asymptote, so on my odd power, I approach negative infinity. And on my even power from the right, I approach positive infinity. How does the multiplicity of the 0 in the denominator affect the graph of r? So if the multiplicity is even, then we approach infinity from the left. If it's odd, we approach negative infinity from the left. All right, so now we're going horizontal or oblique asymptotes of a rational function. We're going to find these guys. All right. If a rational function is proper, so you guys can circle proper because it's one of our vocab, the line y equals 0 is a horizontal asymptote of its graph. A rational function is proper. The line y equals 0 is a horizontal asymptote of its graph. So find the horizontal asymptotes, if any, of the graph. X minus 12 over 4x squared plus x plus 1. Since the degree of the numerator, 1, is less than the degree of the denominator, the rational function r is proper. So if your numerator degree is less than the denominator, then you got a proper rational function. And the line y equals 0 is a horizontal asymptote of the graph. That's kind of important. Make sure you guys highlight that or underline it or star it, because when you do your practice and they're asking you for your horizontal asymptote and this whole proper shenanigans. So the degree of the numerator is less than the degree of the denominator. You get a proper rational function. And the line y equals 0 is a horizontal asymptote. And you guys can definitely graph that with your graphing utilities and double check. That's my suggestion. If a rational function, p of x over q of x, is improper, then it is going to be, when we divide it out, a function with a remainder. What? If a rational function is improper, then p of x over q of x is going to equal a function f of x plus a remainder over q of x. So now we're going to start our dividing, guys. It's going to be great. Let's see what those look like. So if f of x equals b, a constant, then the line y equals b is a horizontal asymptote. If f of x equals ax plus b, as long as a is not equal to 0, then the line y equals ax plus b is an oblique asymptote of the graph of r. In all other cases, the graph of r approaches the graph of f, and there are no horizontal or oblique asymptotes. This is kind of important, 1, 2, and 3. This is how we get our horizontal asymptotes and our oblique asymptotes. All right, so we're going to find the horizontal or oblique asymptotes, if any, of the graph 3x to the 4th minus x squared over x to the 3rd minus x squared plus 1. And we look, our degree on top is higher than our degree on the bottom, so he is definitely not proper. Okay, so just to remind you of long division, I actually put in, when I do this on my own, you put your numerator inside. You have to leave space for the x cubed and the x and the constant. So you're looking at your numerator. He doesn't have an x cubed term, so it has to be 3x to the 4th plus 0x cubed minus x squared plus 0x plus 0. That's how I write it down. It's actually missing here. And then your numerator is on, your denominator is on the outside. So then you ask yourself, you just look at the first terms. So here I ask myself, what do I multiply x to the 3rd by to get me 3x to the 4th? I know I definitely need a 3, and I know I definitely need an x. So then you go 3x times x to the 3rd is 3x to the 4th. And then you do the multiplication. Then you multiply your 3x times your other term. So 3x times negative x squared is negative 3x. And then 3x times 1 is plus 3x. So you want to make sure you're lining up x to the fourth, x to the third, x squared, x. And they did not line that up the way I would have. Hold on. All right, so our function is equal to 3x plus 3 plus our remainder over our original denominator. So we get 2x squared minus 3x minus 3 as our remainder. He goes over our x cubed minus x squared plus 1. So as x approaches negative infinity, or as x approaches infinity, we have a h of x that looks like 3x plus 3. So we can say that we have an oblique asymptote at y equals 3x plus 3. So essentially we ignore the remainder item here and we just look at the function we get out when we do the division. All right, so let's see another example. X squared minus 8x squared minus x plus 2 over 4x squared minus 1. We are going to do the long division. So you say, I multiply 4x squared by what to get 8x squared? I multiply it by 2. So 4x squared times 2 is 8x squared, and 2 times negative 1 is negative 2. I change the sign on both of those, and I get 0 here. Negative x comes down. 2 plus 2 is 4, and so I get negative x plus 4. So this is a case where I get a constant. So I get the full answer is 2 plus negative x plus 4 over 4x squared minus 1. So when we wrote down the rule, we said that our horizontal asymptote would be at y equals whatever our constant is. So we're going to have a horizontal asymptote at y equals 2. And once again, we ignore the remainder rational function because as we get close to infinity or negative infinity, this becomes closer and closer to 0 and does not affect our function. Okay, last example. We have g of x equals 2x to the 5th minus x cubed plus 2 over x to the 3rd minus 1. Let's go ahead and do that long division. Okay, so when we do our division, we get, so we say what times x cubed will give me 2x to the 5th. Well, that's 2x squared. When I multiply 2x squared by x to the 3rd, I get 2x to the 5th. And then I multiply 2x squared by negative 1, and I get minus 2x squared. I go ahead and change the sign. This becomes a minus. This becomes a plus. And this is 0, negative x cubed, plus 2x squared, plus 2. Then I go, what times x to the 3rd will give me negative x to the 3rd? That is a negative 1. So then I get negative x to the 3rd. Negative 1 times negative 1 is positive 1. And then I change the sign. This is a plus. This is a minus. This becomes 0, 2x squared, and 2 minus 1 is 1. So my function, when I do my division, is 2x squared minus 1 plus this remainder. And in this case, we do not have a linear function, nor do we have a constant function. So we can say that there is no horizontal or oblique asymptote. All right, so to sum it up, you guys already wrote all this down, so we're just summing. If n is less than m, the degree of the numerator is less than the degree of the denominator, then it's proper in the horizontal asymptotes y equals 0. If n is greater than or equal to m, then r is improper, and we use long division. If we use long division and we have the same degree, the quotient will be a line, y equals some number, and that's the horizontal asymptote. If n is 1 degree higher than m, then the quotient will be a line, ax plus b, and that line, y equals ax plus b, will be an oblique asymptote. If n is 2 degrees or more greater than m, our numerator is 2 degrees or more greater than the denominator, then we'll have a second degree polynomial when we do the division, and it won't have a horizontal or oblique asymptote. And that's it for today.